Hey again, and welcome back. Today I want to take a look at this module that I got in the last mailbag, which I can link up there. This is a constant current, constant voltage, adjustable buck module. So that means you put a higher voltage on this end, you get a lower voltage on this end, and these pots here let you adjust that. These things are commonly used to charge lithium batteries or to run LEDs. You can also sort of use this as a benchtop power supply, but the voltage will be a bit low on this thing. It is a switching regulator, so that means that the efficiency should be pretty high, but it still can't output that much current. So let's have a look at this. It didn't come with any instructions, and as I'll show you a little bit later, instructions are kind of hard to come by on this thing, but I figured a good place to start would be to take a walk around the device. This is the input side on this side over here, and I soldered some wires to the input and the output. On the input we see there is a diode here. That diode is marked M4, and I do believe that this is a anti-backfeed diode. It doesn't let current come the other way because you can use this to charge a battery. So I believe this is just anti-backfeed, so it'll be biased in the positive direction, in the correct direction. Then here we have a 220 microfarad 35 volt cap on the input, which tells me that the maximum input voltage will be 35 volts, but if I were you, probably keep a margin of safety on that and maybe not go higher than 30 volts. Then down here, I think this is a reverse polarity protection diode. So that one is SS54. That's the input stage. Now for this chip, looks like it's the main chip driving everything here. This is an LM, just trying to see here a little bit better, LM2596S-ADJ. So LM2596S / adjustable. So this here will be doing most of the stuff. Then over here we have a 330 microhenry inductor, which is probably going to be part of the buck regulation. Then over here we have a 78L05, which is a 5 volt linear regulator. And over here on the output stage we have a 35 volt cap. They probably just used the same cap to keep the costs down. And then here we have an LM358, which I believe is a op amp or a comparator, or an op amp in comparator configuration, which seems to be attached to this potentiometer here in the middle. And we can see that the middle pin of the potentiometer, hopefully I'm in focus, comes down and attaches around here, which is around where this LM358, was it? LM358 is. Over here we have an LED, CC, CV, CH, and an OK. So the first thing I would do to take a look at this is we're going to go see the eBay listing. So let me take you over to that. So here is the actual listing for the item that I bought. I bought it from Deep Learnings, although I don't recommend going directly for the sellers that I used, because just because I had a good experience doesn't mean that you're going to have a good experience. But regardless, here's our module here. And you'll see that the instructions here, or the description here, isn't super useful. So fixed turn the lamp current to 0.1 times the value of the constant current. Charge when used to identify whether the battery is full. So I think this here is the key to what one of these LEDs are. I think typically it's like it tells you when the charging is complete. I think so. Increased input reverse polarity protection diode, that would be one of these two or both those diodes. Using dedicated reference IC, high precision sampling resistor so that the constant current is more stable. Yeah, that would be the addition to an op amp on board over here. Particularly suitable for LED driver, high power LED constant current drive. Yep, LEDs do need a constant current driver. Lithium battery charger. Yep, can do that. Including ferroelectric, not quite sure. 4 volt, 6 volt, 12 volt, 14 volt, 24 volt battery charger. I guess in that it doesn't really matter what the voltage is as long as your input is higher. NiCad, nickel metal hydride battery pack charger. Yes and no. Actually, nickel battery charging requires pretty fancy cutoff procedures, so I don't think I'd use it for that. Solar panels and wind turbines. Yes, certainly you can put this in between a solar panel and a lead acid battery, especially since it has those diodes. Specifications. So non-isolated constant current and voltage module. Yeah, important, not isolated. Non-synchronous rectification. Input voltage 7 to 35 volts. Yeah, kind of figured that out by the input cap. Output voltage 1.25 volts to 30 volts. Now that means we need to drop at least 5 volts for the output. Maximum 3 amp current adjustable. Don't know if I'd run it at 3 amps, but we can give it a torture test. Efficiency, that's not too important. Battery use. They tell you some directions here, but I think the important thing here is that you need to know your battery. Then you adjust the constant voltage potentiometer to change the voltage. Then it tells you clockwise and counterclockwise to increase or decrease. Then use the multimeter in 10 amp current scale to measure output short circuit current. So it looks like you have to short the output and then adjust the current. It doesn't tell you which potentiometers do what though. The charge current of transfer lamp default is 0.1 times of the charge current. So that would be, I think that's that one of those LEDs, but I'm not sure. Same thing for constant current driver use, but again they don't tell you which does which and what, right? So yeah, I guess maybe that LED is a dual LED. Red is current, blue is voltage. Not 100% sure really. So when the listing doesn't tell you too much information, you grab the chip off of it and you go find the datasheet. And the reason you find the datasheet is because often these modules are ripped directly out of a typical usage diagram on the datasheet. So here I have a TI datasheet for LM2596. TI has great datasheets. Here, the typical application, and this is a fixed output voltage, so it definitely won't be that, but you do see the 33 microhenry inductor here, so that's good. So let's scroll down. These are datasheets are important information if you're designing or checking the capabilities of your chip, but in our case today we're just trying to look for as much information as possible as quickly as possible. So here we go. So delayed startup circuit, yeah, I don't really need that. Under voltage lockout for buck regulator, yeah, okay. So certain circuits you can implement otherwise. Under voltage lockout with hysteresis, inverting regulator, inverting regular ground reference shutdown, inverting regulator. We don't want anything inverted. We're looking for the circuit that the Chinese company used to build their thing. So here we've got fixed output. Nope, we want variable output. What do we have here? Adjustable output. Okay, so here we have a voltage divider here. So that could be a potentiometer, but it'd be just one, right? And we want to know what's going on. We need to know what all 3 potentiometers do. Keep going down. They have a example of a layout here, very nicely done, and I think that's the end. So we did not find it here, so let's try another company. This one is a ON Semiconductor datasheet, same thing, LM2596, and we're gonna scroll down. There we go, adjustable output voltage version. So let's look what we have here. It looks like we do not have a single potentiometer in here. See, this is a 5-volt regulated output. So they didn't steal it from here. Got the block diagram, a bunch of information. I'm going to keep scrolling. Keep scrolling. What do we have here? Inverting buck boost? Nope. It's pretty nice to know that it does a buck boost. That's pretty good. Inverting buck boost. Buck boost. Buck boost. Negative boost. Lockout circuit. Delayed startup. This is actually kind of an interesting circuit. We might put that together in a future video. There we go. 1.2 to 35 volt. Adjustable 3 amp power supply with low output ripple. Boom. We found a potentiometer here. So this, oh, and look at that, 33 microhenry inductor. The only thing is they didn't put the output ripple filter on. That's a shame. But again, we only see one potentiometer, so it's only really required to have one potentiometer. So the other 2 potentiometers must have something to do with current regulation, because here we see we only have voltage regulation, and the op-amp or comparator, whatever the heck that is, on the board. So I guess from here on we go look at YouTube. So I just did a search here for LM2596, and then I'm going to go down and see one that looks like ours. So I see Andrea Spice has one here that looks identical to ours, but the board is a different color, so I don't know if he's using a different revision. But this one here, Anthony Cartwright, he has one that looks exactly like ours. And so I'm going to click his video, and I have watched it, but I just want to let you know that you should probably subscribe to people who are helping you out on the internet. And let's take the information from this video, which is linked in the description below, back to the bench with us. So I have gathered a few components here, and I'm going to try to give this feed this with a lithium battery. Sometimes switching power supplies don't interact well with each other. I've been given crap about that multiple times in the past, so you happy now? I'm using a lithium battery. However, this is not fused, so I have soldered a fuse onto a little bit of wire here, and I'll be using that to poke into there. So it'll be fused. Now, I think the most prudent thing is to do an open circuit voltage test here to make sure that our voltage isn't too high. Set it to what we want, and then mess with the other pots. Now, I saw in a YouTube video that how the pots worked was this one here. This one here is the voltage adjust, this here is the current adjust, and I guess we'll have to figure that out, make sure it's true. So here we are in voltage, we've got nothing, so I'm just going to stick my negative lead into here. And my positive lead into here. Could arc. Okay. So right now, just gonna bend this like that. There we go. So the OK is on, and no other lights are on. And let's turn the first potentiometer to the left. Turn it counterclockwise. And yeah, the voltage is dropping. So I think I want about 9 volts for the LED that I want to use. There we go, 9 volts. So that's good, we have 9 volts. Now, in order to set the current, it said short the output on 10 amp mode. So I have here my multimeter goes up to actually 20 amps. I don't know if that's a good thing or a bad thing, but I will put it in current mode. And what do we have? Okay, 13 milliamps. And now you see it's in constant current mode. So now I'm going to turn this until we get maybe, let's say, 100 milliamps. Oh yeah, that responds very quickly. There we go. 100 milliamps. Now about that middle one, so what happens is when you charge a lithium battery, the voltage should stay the same. Oh, that current is going all over the place. The voltage should stay the same, so 4.2 volts is your maximum on a single cell usually. Some of them are a little bit higher. And because the voltage has to stay at a maximum, as the voltage in the cell comes up, the current will actually start dropping down, because simply the bigger the differential between the voltages, the more current will flow. So as those voltages come up to roughly the same level, what will happen is the current will decrease. And that's a good way to know if your lithium batteries are finished charging, is when your current is about 1/10 of how you started. So that means your lithium batteries are in top-up mode, and they'll charge extremely slow and you won't get all that much capacity out of it. So I think that's what this one is for, the middle one. If I spin that, I should be able to affect the OK light. Yeah, I just went counterclockwise a few turns, and the OK here has been turned off. Now if I go up a little bit, you'll see it'll turn back on. Yeah, there it is, it's back on. If I shade it a little bit, you might be able to see it better. But if I go a little bit further with it, there it gets brighter and brighter and brighter. So basically, if you're not charging lithium batteries, you can leave this one alone. So that's good. The current did climb a bit though, and I'm just wondering, it seems to have to do with me discharging this inductor or changing the inductance on this, or maybe it pulses. I'm not sure, but the current on this is not 100%. I'm actually going to wind that down a little bit. So I got between 80 and 100 milliamps there. Okay, so that's good. So now, if we unplug this, we should be able to run a LED from this. So here's my LED. This is, I think it's 9 to 12 volts and up to 250 milliamps, I believe. So use these quick connectors here. So this would be used like, let's say you have a laptop power supply, like usually 18-19 volts. You would feed it into here, and then you could run these LEDs ad infinitum, because you'd be well within the rating of all your devices here. Now, I'd like to stick this down somehow, but I can't really stick it down to the LED because the LED itself might get really hot and melt the sticky tack. You're supposed to run these on a heatsink, just by the way. Is this in view? This is in view. Okay, I'll tie up to here. I want to check the voltage coming in. You're supposed to solder these LEDs directly to the actual LED, by the way, not these little tabs. These little tabs, I believe, is just to tie them together in manufacturing. Okay, it's okay if it's not pointed straight to the camera. And let's contact. Okay, well, looks like the device is running. I'm not getting any voltage out to the LED. Something is wrong with my connections here. Oh, well, I'm not getting any voltage because I'm in current. I was shorting that. Well, there we go. Always reset your leads, ladies and gentlemen. So there we go. So we got 8.5 volts that are coming through here because our LED is drawing the maximum current, which should be roughly, I don't know, 80 milliamps when we left it. So it's dropping the current so that we don't go over voltage, or it's dropping the voltage so we don't go over current, I should say. So this is working fantastically, and that means I don't need to put a resistor in line with this LED, and it shouldn't heat up to, oh, that scared me. When you're expecting something hot and then you get something, a sudden burst of sound like that. So yeah, this LED is not getting hot at all. The light output is actually pretty decent, and not like super bright, but quite bright anyways. I don't know if you can see the inside of my palm there. It is blinding me. And this LED will probably run forever like this. So a little couple dollars worth of a module here, a power supply of some sort, and an LED, and you can actually run this quite efficiently. I'm sure this this battery would last quite a while just powering this one little LED, because if we're getting about 80 milliamps of current, times that by 8.5 volts, this is 0.68 watts of power dissipation. In fact, you should actually do that calculation of the input, but regardless, it's probably like 3/4 of a watt. So that's pretty neat. And I think this LED is a 5-watt jobby. So running it at this low of current will make it last forever. And then also, if you want to tweak things, you can always bring up the current like so, and now our voltage is going to end up maxing out at some point. Let's see, now it's more current is flowing, this thing is brighter, and now this will start heating up. Still not too bad actually, still pretty cool. So yeah, this is just the quick look at how this thing works, and it seems to work fantastically. I think I'm going to order a couple more, and there's a few other designs that I like that I might order, so look for that in the future. But for now, this should get you going. Thanks again for watching.